Hello class, in this module we will cover antiviral agents, and rather than trying to cover all the possible agents, we will just focus on two diseases, the flu and HIV or AIDS. So before we even start, I want to reiterate that we don't really have very good treatments for many diseases. I think the only ones that are curatives are the one for hepatitis C, and HIV antivirals also are pretty good at keeping the disease in check. But in general, the main thing we can do for viral infections is vaccination. So let's look a little bit at the variants. Viral particles are very different in their shape and in how they organize themselves. In general, they can have polyhedral, helical shape or cylindrical shape or complex, right? Like the bacteriophages, which infect bacteria, which have a polyhedral sphere, capsid, connected to a cylindrical portion and what looks like legs really. And this lower portion is in charge of attaching itself to the host cell, the viral host cell. So as we were saying, vaccination works very well for several viruses. It's important to use it in a preventive manner, so vaccination doesn't work after infection, and it works very well for viruses like rubella, polio, measles, HPV, and others. And it pretty much wiped out those diseases from Earth almost. It's limited effectiveness with certain viruses like influenza, which mutates very rapidly, which is why we need to repeat the vaccine every year or 2 years at the most. It's not possible for all viruses. For example, we don't have one for HIV, for RSV, and for cytomegalovirus. So vaccination is the first line of defense, and it's very important to remember that it's also the only effective way. Like, for example, we read now in the paper about the recent epidemics in Washington State and of measles, due to the fact that compliance with vaccination has gone down. The problem with that is that if a person acquires measles, we still do not have antiviral agents that can combat the infection, and so doctors will rely on what they call comfort or supportive measures rather than trying to cure the disease. The most important thing to remember about viruses is that we can classify them by their nucleic acid, and so they are very different. Some of them have single-stranded RNA, and that can be either positive sense, meaning is the same sense as messenger RNA, or negative sense, and so that we are required to be replicated. The way they work is that somehow they all have to translate their nucleic acid into messenger RNA, typically going through DNA, but not necessarily. And so one of them is, for example, lentiviruses such as HIV has a positive sense RNA, but needs to be converted to DNA via this reverse transcriptase enzyme. We also have double-stranded RNA viruses, single-stranded DNA viruses, and double-stranded DNA viruses. And so, by this classification, we can also subclassify the viruses by the shape of their capsid and whether they are enveloped or not. Enveloped meaning that when they bud out of the host cell, they take part of the membrane with them. Another way more intuitive to see the complex slide we just saw is to focus on messenger RNA and then see all the ways by which viruses can convert their nucleic acid to messenger RNA. So for double-stranded DNAs, that can be direct. For single-stranded RNA, then we go through a DNA-RNA hybrid and then double-stranded DNA, and that's done by enzymes called reverse transcriptases, and so on and so forth. So you got the idea, everybody has to make messenger RNA encoding for viral proteins, and they do it by several routes. And that's important because in some cases that will mean that we have specific enzymes that we can target in antiviral therapy, and we'll see that in HIV, for example. So the common viral pathogens for which we have antiviral drugs are herpes, RSV, influenza, hepatitis B and C, and HIV. And actually HIV is the one for which we have the most rational development of drugs. And that was due to the emergence of the virus in the late 80s, early 90s, and the deployment of a large amount of research money in order to investigate the virus. And so that resulted in structural analysis of the viral proteins and the discovery of many targets. The other way of thinking about combating a disease, a viral disease, is to think about all the steps that viruses have in common, even though they do it with very different ways and very different proteins. And so all viruses need to absorb to the target cell. They need to enter it. Typically, they need to uncoat, so they need to shed the protein capsid. And then the nucleic acid needs to be transcribed somehow into a messenger RNA and then translated and transformed in protein. From protein synthesis, the viral proteins often need to be processed. And we'll see that enzymes in charge of processing viral proteins are the target, for example, of anti-HIV protease inhibitors. Then the virus needs to assemble inside the cell and needs to be released. And so Relenza and other Tamiflu address that step in the flu virus and prevent the release of mature variants. And so let's look at the antivirals then by life science, so by this life cycle. So we have agents that act before cell entry, and so they target the virus-associated protein by mimicking it and binding to the viral receptor, to the cellular receptor, or vice versa, they mimic the cellular receptor and bind to the viral protein. And then we have entry inhibitors, and those are quite important for HIV. We have uncoating inhibitors, such as amantadine and remantadine, which are being used for flu, and those will cover. And then for viral synthesis, so protein synthesis in general, we have inhibitors that target reverse transcription, integrase, transcription, translation, and also some that target mRNA directly. We also have protease inhibitors that basically interfere with the processing of the viral protein, and antivirals that interfere with viral assembly and viral release. So with that, let's move on to the first line of thoughts, and so we'll cover next viral agents that target influenza virus.